Example 26. Example 26 asks us to find and classify the stationary points and points of inflection of y is equal to 3x to the fifth minus 20x to the third. Alright, so y is equal to 3x to the fifth minus 20x cubed. So dy by dx would be equal to 15x to the 4 minus 60x squared. Now, first, let us find the values of x at the stationary points. At stationary points, dy by dx is equal to 0. So dy by dx, which is 15x to the 4 minus 60x squared is equal to 0. Divide the entire equation by 15. So we now end up with x to the 4 minus 4x squared is equal to 0. Factor out x squared, we end up with x squared minus 4 is equal to 0. Factorize x squared minus 4, which is the difference of 2 squared, we get x squared, x plus 2, x minus 2 is equal to 0. So now we have x squared is equal to 0, x plus 2 is equal to 0, and x minus 2 is equal to 0. Therefore, x is equal to 0, or x is equal to minus 2, or x is equal to 2. So these are the values of x at the stationary point. These are the values of x at the stationary point. We need to classify, what type of stationary points these would be. To do that, I'm going to use the second derivative test. Alright, so first derivative is dy by dx is equal to 15x to the 4 minus 60x squared. So let's differentiate d2y by dx squared. Alright, this would be equal to 60x to the third minus 120x. 120x. Alright, now let's test what stationary point, or let's classify the stationary point at x is equal to minus 2. So when x is equal to minus 2, d2y by dx squared is equal to 60 minus 2 cubed minus 120 times minus 2. So this is going to come out to be 60 times minus 8, which is minus 480. Negative here times a negative is a positive 240. So this is equal to minus 240. So here d2y by dx squared is less than 0. So at x is equal to minus 2, there is a maximum turning point. All right, let's go back up, utilize this page as much as possible. Start back again with d2y by dx squared, d2y by dx squared is equal to 60x to the 3 minus 120x. Now, when x is equal to 2, d2y by dx squared is equal to d2y by dx squared is equal to 60 times 2 cubed minus 120 times 2. So again here we have 480 minus 240, and this is a positive 240. Positive 240, so d2y by dx squared is positive. When d2y by dx squared is positive, we have a maximum turning point. So at x is equal to 2, there is a maximum turning point. All right. Now, let's see what happens when x is equal to 0. When x is equal to 0, d2y by dx squared would be equal to 60 times 0 cubed minus 120 times 0, which is 0. Alright, now when d2y by dx squared, when d2y by dx squared is equal to 0, you could have a point of inflection, but it's not necessarily a point of inflection, but you could have a point of inflection. So in order for you to, what you'd have to do, well, we know for one thing that it's neither what a maximum nor a minimum point. So it actually could be a point of inflection, but we're not sure. In order to be sure, we'd have to do first a further test. We could go back to the first derivative test. Fine, we could go back to the first derivative test. We could also look at the whole issue of what concavity, the concavity before and the concavity after. All right, so we probably could look at that, but let's do something else first. Let us determine the values of x when d2y by dx squared is equal to 0. We actually know one of them already, that when x is equal to 0, d2y by dx squared is equal to 0. But if we remember carefully, at a point of inflection, at point of inflection, d2y by dx squared is equal to 0. So therefore 60x to the 3 minus 120x is equal to 0. Divide the entire thing by 60. If we do, we're going to end up with x cubed minus 2x is equal to 0. Factor out x squared minus 2 is equal to 0. Therefore, x is equal to 0, or x squared minus 2 is equal to 0. Therefore, x is equal to 0, or x squared is equal to 2. So, x is equal to 0, or x is equal to positive and negative 2. So these are the values of x for which d2y by dx squared is equal to 0. As I said, we actually knew one before. We knew that at x is equal to 0, d2y by dx squared is equal to 0. So now we also know that at x is equal to what? Positive, negative. It should be positive and negative the root of 2. At x is equal to positive and negative the root of 2, d2y by dx squared is equal to 0. So we need to check each of these to see at which one there is a point of inflection. Alright, so to do that we have to check the concavity. So at x is equal to 0, let's see that one. At x is equal to 0, we have d2y by dx squared is equal to 60 x cubed minus 120 x. So it's not so much at, I want to say, so we're looking at, all right, let's write it back, at x is equal to 0. So let's check a value of x before 0. I could say when x is equal to minus 1, d2y by dx squared would be 60 minus 1 cubed minus 120 minus 1. So this is going to be minus 60 plus 120, and this is equal to 60. Alright, so this is positive. So if this is positive, what we have is concave up. So at x is equal to minus 1, the function concave up. I'm going to say when x is equal to 1, d2y by dx squared would be equal to 60 times 1 cubed minus 120 times 1, which is 60 minus 120, which is equal to minus 60. So at x is equal to 1, the function concave down. Therefore, at x is equal to 0, there is a point of inflection. All right. We could now also check now for the point at, let's say, at x is equal to the root of 2. Let's try minus the root of 2 first. Minus the root of 2. Now minus the root of 2, let's get the approximate value of that. So the root of 2 is approximately, this is minus 1.4. Alright, let's check the concavity before and the concavity after. Some of it you already know. Let us say at x is equal to minus 2, d2y by dx squared was equal to minus 240, I think. Minus 240. We did that on the previous page. Minus 240. So this is what concave concave down, and at x is equal to -1. So -2 is just before minus 2.4, 1.4, and -1 is just after. And we have these values already. d2y by dx squared is equal to d2y by dx squared. I think we did -1 already. We did when x is equal to -1, we got -60. So it didn't change concavity. So therefore, at x is equal to minus the root of 2, sorry, therefore, there is no point of inflection at x is equal to minus the root of 2. Alright, there's no point of inflection at x is equal to minus the root of 2. There is a point of inflection at x is equal to 0. So let's just do the final one. Alright, at x is equal to the root of 2. I'm going to say, so the root of 2 is, let's say, approximately 1.4. So we can test before and after it. I think we already tested when x is 1. So when x is equal to 1, d2y by dx squared was equal to, when x is equal to 1, was equal to -60. So -60 is concave down. We also did when x is equal to 2. When x was equal to 2, we got, when x is equal to 2, I think we did that on the page before, so let's go back and have a quick look at it. When x was equal to 2, d2y by dx squared. So when x is equal to 2, d2y by dx squared is equal to 240, which is positive. So d2y by dx squared is equal to 240. 240 means concave up. So at x is equal to the root of 2, the function changes concavity. So at x is equal to the root of 2, there is a point of inflection. All right. So we had 2 turning points, and we have, for this function, we have 2 turning points and 2 points of inflection.